Hello dear students, welcome you all. In this lecture, I am going to discuss about the distribution of n distinguishable particles in k compartments of unequal size, right? Which are further divided into small cells of equal size, right? So this is the topic for this lecture. So here in this lecture, we will discuss the distribution of n distinguishable particles, right? So the first thing here is that is the number of particles are n and they are distinguishable, distinct particles, right? Now the second thing is we are going to distribute these n particles in compartments, k compartments, right? K compartments, but the condition is all the compartments are of unequal size, right? Number two condition. Number three condition is all these compartments, clear, are further divided into small cells of equal size, right? Cells of equal size. So these are some important points that we have to remember during the discussion of this entire topic, right? So suppose we are given a volume, right, in which we are going to distribute these n particles, right? And that the given volume is divided into k compartments of unequal size, right? So let's select the given volume. Here we are using the two-dimensional, system for representation of this volume. So I'm obviously using this, you know, rectangular compartment, right? And I'm saying now given area, clear? But the thing is clear that we have a box, three-dimensional box, right? Now this is the given area. I'm going to divide this area into small compartments of unequal size. This is compartment number one, clear? This is compartment number two, right? This is compartment number three, clear? This is compartment number four, right? And this is compartment number five, right? So, and this is the compartment number six, clear? Similarly, this is the kth compartment, and this is a k minus 1th compartment, right? So now, what we did, we divided the given area into different compartments of unequal size. This is first compartment, this is second compartment, this is third compartment, this is fourth compartment, this is fifth compartment, this is sixth compartment, this is kth compartment, this is k minus 1 compartment, right? Here we have to distribute these n particles which are distinguishable, right, into all these compartments, right? So first of all we have to think, can we apply principle of equal priori probability here? Principle of equal priori probability. So principle of equal priori probability means something that exists in our mind prior to the this experiment, prior to this distribution. So prior to this distribution, if all the compartments are of equal size, then we have to assume that the probability of the particle entering in any compartment should be equal, right? This is the principle of equal priori probability. But here in this particular case, you can see all the compartments are of different size, right? So when they are of different size, we can't apply this principle of equal priori probability here, because the size is unequal, right? So in order to apply principle of equal priori probability, we have to further divide these compartment into small cells of equal size, right? So I'm going to do it. I'm going to divide these compartments into small cells of equal size, right? So you can see now we have small cells of equal size, right? You can see here I have divided all the given area into different number of small cells, right? So and the k minus 1th compartment, right? So here you can see clearly that what I did, I simply divided the these different compartment into these small cells, right? These are the small cells, but one thing is clear that all these small cells are of equal size, right? Now we can apply principle of equal priori probability when I am distributing some number of particle in the given compartment. In that case, suppose in the first compartment there are n1 particle, for example. Then when the n1 particle, sorry, will go into the first compartment, they have equal probability in entering any of this small cell. Similarly, in case of second compartment, let the number of particles are n2. Clear? So obviously, again, then the number of particle n2 going in the second compartment will have equal priori probability in entering any of the given cell, small cell, right? So this is same for all other compartments also. Let in the first compartment we have a Z1 number of cells. Similarly, in second, let we have a Z2 number of cells. In third, we have a G3 number of cells. Here Z4, here Z5, here Z6, here ZK, and here it is ZK minus 1. This is what? This is the number of cells in the given compartment. Now here, there is one more restriction. There is one more condition that when we are distributing, suppose n1 particle in Z1 cells of first compartment, there is no restriction on the number of particle entering in any cell of the compartment, right? Even the first cell can accommodate as much number of particle as it can, right? The particle are distinguishable. So all these conditions are applicable in this particular case. Now, what is the task, ultimate task that we are going to do? We are going to find the thermodynamic probability W for the macro state N1, N2, N3, so on Nk, right? It means what we are considering? We are considering N1 particle in first compartment, N2 particle in second compartment, so on N k minus 1 particle in this compartment and nk particle in this compartment. You know, there are different possibilities. Even one particle can enter in one compartment, no particle can enter in second compartment. Similarly, all other possibilities are there, but we are considering one among them, and that possibility is this. Clear? Now we are finding the number of microstates. Clear? Total distinct arrangements, meaningful arrangements in this particular macro state. That will called as the thermodynamic probability. We know thermodynamic probability is defined as the number of microstates in the given macro state, or the number of meaningful arrangements. Now to calculate this number, let's start from the first cell. Clear? Now the first compartment. Sorry, in first compartment we have how many cells? G1 cells. And how many number of particle? N1. Right. Now, suppose I want to arrange one particle out of these N1 particle in a G1 cells. So, in how many ways I can do it? Obviously, G1 ways. Similarly, I want to arrange the number 2 particle of these N1 particle in G1 cells. In how many ways I can do it? Obviously, G1. So, similarly, if I continue, I will get here in G1, obviously, again G1. So, the total number of ways in which I can arrange N1 particle in G1 cells will be obviously equal to G1 power N1. Right. So, this is the number of ways of arranging N1 particles, N1 distinguishable particles in G1 cells. Right. It is quite obvious if you have remembered the distribution of 4 particle in 2 compartments. Right. In that case, the total number of microstates were how much? 2 raised to power 4. That is 16. So same logic is applied here. Particles are of the same nature. They are distinguishable. Right? Here the number of compartments, I mean cells, is equal to G1 and the number of particle is N1. Right? So same analogy is here. This is for the first compartment. Similarly, if I go to the second compartment, then for the second compartment, it will be G2 and N2. So obviously in this case, the total number of ways will be G2 power N2. Similarly for third compartment, it will be G3 N3. And the total number of ways, G3 power N3. Similarly, so on for the kth compartment. What will be the number of ways? Gk power Nk. Right. Now this is one thing. Now again come back to the first compartment. Clear? Again come back to the first compartment. Now this is what? In case of first compartment, I have found the total number of ways of distributing N1 particle in a G1 cells is equal to G1 power N1. But here there is one more twist. I have to select N1 particle out of the total N particles. This is also the case. How we can select N1 particle out of N particle? Suppose I have 10 particle, right? For example, and I want to select 2. In how many ways I can do it? Obviously 10C2. So here it will be NC N1. 10C2 means NC N1. So it will become N factorial divided by N1 factorial into N minus N1 factorial. So this is what? This number is what? This is giving us the number of ways, right, of selecting N1 particle out of the total N particle. So now the total number of ways, now the total number of ways of selecting N1 particles out of N particles and then distributing them in first compartment having G1 cells. It will be obviously what? It will be obviously this figure multiplied by this figure. Clear? So let it is x1, right? Let it is I am representing it as x1. Clear? X1 is equal to NC N1 multiplied z1 power n1, right? So it is equal to n factorial divided by n1 factorial into n minus n1 factorial into z1 power n1. Similarly, for the second compartment, same logic. Now here, in case of second compartment, n is not same. Why? Because we have already taken n1 particle out of the n particle, and we have put them in the first compartment. So the number of particles that are left up with us are n minus n1. Then c n2 into z 2 power n2. So it becomes how much? N minus n1 factorial divided by n2 factorial into n minus n1 minus n2 factorial into z2 power n2, right? Similarly, for the third compartment, what will be the result? Now it will be n minus n1 minus n2, because these n2 particle are also taken from it. C n3 into z3 n3. So it will become n minus n1 minus n2 factorial divided by n3 factorial into n minus n1 minus n2 minus n3 factorial into z3 power n3. So in this way you can continue and you can find out xk for the kth compartment, right? So now all these are what? X. What are these x? These are the number of ways, meaningful, right, of arranging different these like n1 particle in z1 cells, n2 particle in z2 cells, with the total number of ways of selecting these particle out of a n particle, right? So the total number of ways, that is w, n1 n2 n3 so on nk, that is thermodynamic probability, total number of meaningful ways, it will be equal to x1 multiplied by x2 multiplied by x3 so on multiplied by xk, right? So when you will put the value, you can see when you will put the value, what you will get when you will multiply this with this factor will get cancelled with this factor will get cancelled with the next factor, this similarly it will cancel with the next factor in the x4 tab. So this thing will continue, and ultimately what you will get, it is equal to n factorial divided by n1 factorial into n2 factorial into n3 factorial so on nk factorial into z1 power n1 z2 power n2 z3 power n3 so on zk power nk. This is w, right? So if I go further, right, so I can write it w is equal to n factorial, right, into multiplication symbol, I go from 1 to k, right? Here we have zi power ni, right, denominator ni factorial, right? So this is the given thermodynamic probability for what my macro state, that is w, n1 n2 n3 so on nk, right? N factorial, I go from 1 to k, zi power ni divided by ni factorial. So this is the required thermodynamic probability, or the required number of meaningful arrangements of n1 particle in g1 cells, n2 particle in g2 cells, and all that, right? So this was the entire discussion about the distribution of these undistinguishable particles in k compartments of unequal size. These compartments are further divided into small cells of equal size, right? So this is all about it. Now, what is the importance of this article? This article is very, very important because we are going to use it in the derivations of distribution law of three wings of statistics, that is Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac. Clear? So this is the application of this distribution. Not distribution. Sorry, this is of thermodynamic probability, right? This formula that we have derived, right? And this is one, right? So this is all about it. Thank you very much.